Despite all the efforts applied by project managers and systems engineers, it seems that projects have an alarming rate of failure. In fact, as we see later, by standard definitions, almost all projects fail. Now, there are many detailed views of what might contribute to that failure, but it's very useful to take a view of the problem from the highest level perspective. When we do, a remarkably simple observation can be made, and the principal cause of project failure becomes very clear. Here are a few examples of the magnitude of failures in projects. You can see alarming evidence of large overruns in both cost and schedule. I've only chosen a few here, but similar statements can be found in the literature of hundreds of peer-reviewed articles. We won't labour the evidence, but I'll return to the last two examples later. The first is that the Chevy Volt, an electric car based on an existing traditional design, doubled in manufacturing cost during design. And the second is that NASA's projects that have been successful in meeting their requirements have an average cost growth of 47 to 61%. Now, if you bear with me for the moment, let's accept the proposition that project failure is commonplace. If you do have any doubts about that, a quick Google search should quickly remove them. Well, if project failure is commonplace, well, who's at fault? Is it because project management and systems engineering have failed? Are those disciplines useless? Do they have no purpose whatsoever? Well, to look at that more carefully, we have to understand what is it we mean when we say that projects have failed. And then, understanding what that failure is, we could then go back and look at the root causes of that failure, and then we might be able to determine what role project management and systems engineering could have had in that failure, and therefore we could learn something and maybe be able to improve those disciplines, and maybe projects might then be more successful. So let's start then with the first of those issues, because we do need to be clear as to what we mean by project failure. Well, almost all in the space would agree that projects fail when they don't deliver on time, on budget, and to the quality expected. Research indicates that 85 to 90% of projects fail to deliver against those criteria. Now, that really is a large proportion of projects, which reinforces our earlier assertion that almost all projects fail. Now, that's quite an alarming thing. So let's look more closely at what reasons there may be behind that failure. Now, I'm going to show you a number of reports, or the output of a number of reports, which talk to project success factors or reasons why projects fail. The first of those is a major report which comes out annually. It's a very important report and it contains a very large amount of information. And I'm extracting here just a very few of those aspects. But you can see that when it talks to the top 10 project success factors, it identifies the first as being the business not encouraging users to be involved, that the management from the business doesn't support and buy into the project, that the business doesn't provide a clear statement of requirements for the start point for the project, it doesn't plan the project properly, it has unrealistic expectations of the project, it doesn't set milestones properly, it doesn't engage competent staff and encourage competent staff, it doesn't take ownership of the project nor its outcomes, it doesn't have clear vision and clear objectives, and it doesn't hire hard-working staff. If we look at Camilleri, for example, identifies a series of reasons for project failure, and again you can see a lack of a valid business case, the business not defining objectives, the business not communicating, not selecting stakeholders properly, not managing the stakeholders, that the outcomes and the benefits were not properly defined by the business in measurable terms, the business lacked any quality control, accepted in the first instance poor estimation of duration and cost, had inadequate governance, and then basically contributed by not planning sufficiently and coordinating the resources required for the actual project. If we look at the report that came from the Lean report on project management, it identified 10 top challenge themes. Firstly, the business being reactive in project execution, the business not setting requirements again properly, the business not having sufficient alignment between the project and the enterprise, not integrating the processes across an enterprise but optimising them locally, having unclear roles and responsibilities and accountability of the management of the project, mismanaging program culture, competence, knowledge, insufficient program planning, having improper metric systems, KPIs, lacking proactive program management, poor program acquisition and contracting processes within the organisation. So what role then does project management and system engineering have in that failure? Well, you can see clearly almost every aspect of any of those lists is fairly and squarely the province of the business and of the organisation's leadership. Let's call them business management. They're not the responsibility of project management nor of systems engineers. Now, any of those factors that could be considered to be within the bailiwick of project management and system engineering to some degree, so things like quality control and estimation of duration and cost and so on, they're then dominated by management actions. If the milestones aren't set properly, if the adequate resources which are asked for are not applied, then regardless of any assiduous application of project management and system engineering, the project will still fail. And so it's obvious in that list, and there are many other lists, and I say a quick Google search, you'll find many other causes of failure, but you'll find that the principal causes of project failure are largely outside the control of project management and systems engineering. They are fairly and squarely failures in business management. In fact, the opposite is true. If we look then at project management and systems engineering, we can see there is considerable evidence that those two disciplines actually have a positive effect on project success. So that research has shown that for projects that have met or exceeded expectations, that is in schedule, budget and satisfying technical requirements, projects of all complexities benefit from strong system engineering practices, but the challenging projects have even greater impacts. That the higher requirements, development and management capability is strongly associated with a better program performance, that challenging projects perform better. Perhaps the most persuasive evidence with regard to systems engineering is provided by data from NASA, and that is projects that expended the industry average of 2 to 3% of total project cost on the requirements process experienced cost overruns between 80 and 200%. Projects that invested 8 to 14% of their total project cost or effort in the requirements project had 0 to 50% cost overruns. Clearly, we know how to ensure that projects are successful, but yet all projects fail. That brings us back to the question, how is that so? Why do they fail when we know how not to make them fail? To focus on that, we have to come back up to the top and let's revisit our definition of project failure. And we note that projects fail when they don't deliver on time, on budget, and to the quality expected. That is, to the time, budget and quality that we estimated that was achievable when the project was established. That's an interesting observation. Let me give you a little pop quiz. So let me ask you a question. If a project takes half the time and costs half that which was originally estimated, what's the problem? The answer? Well, clearly it's a failure in estimation. The next question is, though, if a project takes twice the time and costs twice that originally estimated, what's the problem? Well, clearly it's a failure in the project. The project has failed to deliver on the time and cost estimated. Now, clearly those two things can't both be true. So let's revisit our project failure. So it's really quite remarkable when you think about it. What we're saying is that failure is defined not by what we did, nor how well we did it, but what we thought we were going to do at the outset. That's not project failure, that's project estimation failure. Remember the two examples that I highlighted at the start. The first was that the Chevy Volt doubled in manufacturing costs during design, but that was because there was a significant effort that our car manufacturer, who was very good at manufacturing cars, didn't understand because they were designing an electric car for the first time. It's hard to imagine any car manufacturer estimating the cost of manufacture of an existing model with less than 5% accuracy. So why is there a difference? Why is it that the estimation of a small novel change to the car led to some considerable estimation failure? Well, we underestimate because at the point at which we estimate, we can never know exactly what work needs to be done unless we have done exactly that work before under exactly the same conditions. If we look at our ability to estimate in the context of the system lifecycle, we can see why a car manufacturing company can reliably estimate the cost of manufacture of a current car. At the critical design review, at the end of design, before we go into construction and production, we have a detailed work breakdown structure, a parts list, evidence of production times and costs, and so on. In short, the only contingency we need is 5% or so to account for the causes of excusable delay, parts shortages, labour shortages and so on. If we now come back one review earlier, at the preliminary design review, at the end of the subsystem level design, we do have an outline work breakdown structure, but we've not done the lower level design. So we don't have a detailed parts list. We don't even have a detailed design. We have little production experience because we've not yet run these prototypes through a production line. So we need about 20 to 30% contingency to account for the detail, which we will discover when we put our engineers onto the detailed design and development activity. Let's now come one review before that, and we come up to the system design review, where we're considering a system design at the system design level. We're talking about a functional design now. We not even have a physical architecture yet to guide our estimates. We may have some early system prototypes and some exemplar solutions and some experience behind us, but we still need 40 to 50% contingency in the estimate that we make at the functional architecture that we have available at the system design review. If we come back then even earlier still, when the project is proposed and approved by the board, by management, we normally only have a loose set of business and stakeholder needs, and we haven't even developed the system requirements yet. We therefore need some 60 to 100% contingency. Note that that lines up with our observation that most projects are run over by a factor of, well, that amount. And also while we're here, these observations raise the question of when should a customer sign a contract? When should a customer engage with a developer through a contract, particularly if we intend to use a firm fixed price structure to mitigate risk? Well, it's quite clear that if we engage at the project proposal level, we need serious contingency, and it would be almost suicidal to sign a fixed price contract for work which is so loosely proposed. As we come further and further down the system life cycle, we can see that our confidence in a fixed price would significantly increase, but we really don't have any significant confidence in it until we get to the critical design review at the end of detailed design. It makes little sense then to sign a fixed price contract at system design review when the project is so poorly formed at that point. Now let's look at that point a little bit more closely. The second example we highlighted at the start was NASA's development projects that have achieved the required quality and have historically then done so with an average cost growth of between 47 to 61% over that which is originally estimated. Now this is over projects largish, smallish, across all types of domains and all types of technologies. And so what's interesting about that is the solution to NASA's problems is immediately obvious. All NASA has to do to avoid project failure is to multiply all future cost estimates by a factor of 2, or at least 1.61, and all projects will be the darlings of management because they'll come in within budget, and some will even have an underspend of up to 15%. And the real problem, therefore, is abundantly clear. The problem is not that we can't manage project. The problem is that it's not that we don't know how to do project management and we don't know how to do system engineering. The problem is that we have no idea how to estimate projects properly. And then management won't provide the constructs within which those estimates can be adjusted properly with time. So if the solution is as simple as doubling the estimates, why don't we do that? Well, again, we come back to business management and the maturity with which most organisations approach their projects. Can you imagine in your organisation what would happen if the estimates for most projects were doubled? They were not likely to get approved. Yet business seems quite happy with the certainty that almost all projects will fail and exceed their original estimates by a factor of 2 or more. So let's conclude by going back and looking at the questions that we asked originally. Firstly, project failure is now commonplace was our original assertion. Actually, really, project failure will still be commonplace because little is being done to address the root causes of failure. And to be frank, whilst project management and system engineering are working very hard as disciplines, the point with which they can actually have any effect on the causes of project failure is now out of their control. It belongs to project management. The second issue was, so what are those actual causes of project failure? Well, we've seen the actual causes of project failure are principally failures in business management. And until business management recognise that and drive projects as their projects, not hand off the projects to project managers and system engineers to take responsibility, until that point, projects will still continue to fail. The impact of project management and system engineering on project failure? Well, we've seen that it actually has a very positive impact, but it can't have any great consequence until business management pay much more attention to their contribution to a project and take ownership of projects and any subsequent project failure. Well, if you're interested in this and similar topics, you may also be interested in the Capability Systems Centre at UNSW Canberra. The centre is an independent think tank that offers cutting-edge research and analysis to government, defence and to industry. If you are after more information, please visit our website. You may also be interested in these two texts, System Engineering Practice and Requirements Practice. Both are available in paperback form from the Amazon websites or the publisher Argos Press websites.